Now, just to make sure all these connections are clear, let's evaluate 7C4. Now, there's still some questions in class about how you evaluate this. I said 7C4 is 35. You should be able to write down the definition of NCR and then see that N is 7, R is 4, so we plug in 7 for N here and here. We plug in 4 for R here and here. Now, I did see a couple of instances where people had the formula and they had it right, but they plugged in N. They plugged in 7 instead of 4 for the R here. So that's kind of a fatal mistake. And another fatal mistake we'll talk about in a second. Okay, so if we plug in 7 for N and 4 for R, you should easily be able to verify that what we get is 7C4, which is 7 factorial over 4 factorial times 7 minus 4 factorial. And of course, then 7 minus 4 being 3, that gives us 7 factorial over 4 factorial times 3 factorial. Now, one thing you absolutely don't want to do is you don't want to say 4 factorial times 3 factorial is equal to 12 factorial. If you want to convince yourself of that, figure out 4 factorial, figure out 3 factorial, that's going to be 24, that's going to be 6. You multiply them, you get 144. If you do 12 factorial, 4 times 3 factorial, 12 factorial is going to be what? It's in the 400 million range, okay? Not anywhere close to what you get if you do 4 factorial times 3 factorial, so don't make that mistake. I saw a number of errors in evaluating this. You want to be very careful, okay? So if we apply the definition, this is what we get. We subtract 4 from 7, we get 3, so we have 3 factorial. Also, don't make the mistake of doing 7 factorial minus 4 factorial. Factorial doesn't distribute over subtraction. Okay, if we write this out now, I'm going to write it out this way. I'm going to write 7 factorial, which is 7 down through 1, divided by 4 factorial. I'm going to leave that as a factorial for the moment. And then times 3 times 2 times 1. Okay? We divide the 3, 2, 1 into the 3, 2, 1. That just gives us 1. And now we have left 7 times 6 times 5 times 4 over 4 factorial, which of course is 4 times 3 times 2 times 1. We can interpret this one in terms of the fundamental counting principle, as we're choosing 4 out of 7, 4 slots out of 7 in this case, in which to put the heads. Here could be one choice. Here are 7 slots, put heads here, 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 and here. Okay? So, there were 7 choices for where to put the first head. All 7 slots were open. We put the first head somewhere, let's say here. Now, there are only 6 slots open for the second. So, we multiply the 7 by the 6. So, let's say the second goes here. So, we've chosen here and here, right? Okay, then 5 for the third. Maybe we choose this one for our third choice. We get the 5 here. And then 4 for the fourth choice, and that would leave us this one out of these 4. So there were 7 times 6 times 5 times 4 possible choices. We filled them with these 4 slots. We filled them in this order, here, 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 and here. There were a number of different orders in which they could have been filled. We could have done this one, this one, this one, and this one, or this one, this one, this one, and this one. There are actually 24 different orders in which those 4 heads could have appeared in these slots. So we divide the 7 times 6 times 5 times 4 ways the slots could have been filled in different orders by the 4 times 3 times 2 times 1 orders in which those same 4 slots could have been filled, and we get 7C4. Now this comes out 35. We can see this easily. 3 times 2 is 6. 4 divides into 4, leaving us 7 times 5, or 35. So 7C4 equals 35. And that corresponds to the number in the 7-flip row in the 4 heads column, 4 heads place. Okay, 0, 1, 2, 3, 4 heads, 35. Now there is another way to think of 7C4, and that's just to reason it out directly the way we did here. And that is to say, well, 7C4, we know there are 7 possibilities for the first, 6 for the second, 5 for the third, 4 for the fourth place in which we put the heads. And then there are 4 times 3 times 2 times 1 ways to order those 4, and we can reason that out directly without going through the formula, but you absolutely want to be able to use the formula. Okay, so this comes out 7 times 5 or 35, as we saw here. Again, this is the number of ways to get R heads on N flips, and to get so many heads on so many flips, the order in which those heads occur, the slot that's filled by that head could be chosen in any order. So this is the meaning of the combination as applies to the question of getting so many heads on so many flips. And that result occurs at a specific place in Pascal's triangle. So if we wanted the number of ways to get 4 heads on 8 flips, we'd go down to the flip 8 column. This would be the flip 7 row, not column, in the flip 8 row, and count over 0, 1, 2, 3, 4. There are 70 ways. That's the same thing we would get if we evaluated 8C4. We would have gotten 70 by using this formula. The Pascal's triangle gives us a quick and short way for fairly small numbers, down to the 10th row or so. It's fairly easy to write out the triangle and get the arithmetic correct. It gives us a kind of a shorthand picture of the number of ways to get different numbers of heads on different numbers of flips. It's not particularly useful if you want to do something involving 25 flips of a coin. The numbers get too big. It's too hard to list a triangle all the way down to there. In that case, you want to use the formula. So you do need to be able to use the formula, but the triangle gives you a very useful picture.